Welcome back. In this section, we're going to do something called usually ANOVA, which is a way of comparing three or more means in a test called the one-way analysis of variance. And where that ANOVA name comes from is the A-N-O and V-A. So ANOVA is analysis of variance. And what it is a hypothesis test for comparing three or more population means. And I wanted us to be sure to get this word population in the notes, because when we're doing these hypothesis tests, we're working with sample data and we're using sample means. But we're attempting to use those samples to find out something about the population. So what we will have in this test is three or more sample means, but the idea of the test is to be able to use those sample means to compare three or more population means. And let me just right off the bat give you an example of what we mean by the setup where you'd want to do this. So a researcher wishes to try three different techniques to lower the blood pressure of individuals diagnosed with high blood pressure. The subjects are randomly assigned to three groups. The first group takes medication, the second group exercises, and the third group follows a special diet. After 4 weeks, the reduction in each person's blood pressure is recorded, and we want to, or the researcher wants to, test the claim that there is no difference in blood pressure reduction between the three treatments. Okay, so we don't just have two treatments here, we've got three or more, and we want to compare the average result of those three treatments. Now, I've mentioned this is going to be a hypothesis test, so here are the hypotheses. Remember, the null hypothesis is always a statement of no difference, no change. So if you can write it out mathematically instead of in words, this is going to be the one that has equal signs in it, the null hypothesis. So I'm going to make up some notation here. Mu sub m, and I'm using mu because that's the standing for the population mean, which we don't know. We'll have a sample mean. We don't know the population mean, but we're hypothesizing or testing whether all three of these means would be the same. And what I'm using here for my notation, I'm letting m be the data with where medication was used. E is the set of blood pressure reductions where exercise was used, and I'm letting D be the set of blood pressure reduction data where the special diet was used. Okay, so the null hypothesis is going to be that all three of those means are the same. And now this is specific to this example, but in general, the null hypothesis will be all means are equal, however many there are, and whatever they are. The alternate hypothesis, that one I can't really conveniently put into math, so we'll just put that in words. The alternate hypothesis, H1, is that, at least one mean is different, not equal. And just as a note, although this is a test that one of them is not equal, and when you write things out mathematically, if you have the not equal sign, this is going to give you a two-tailed, the not equal sign general gives you a two-tailed test. But these ones where we have to say in words that something's different, in general, those have turned out to be a right-tailed test. Now, I'm just mentioning that because I don't want to give the misimpression that this is a two-tailed test when I wrote the not equals there. But we won't actually have to worry about this because technology is going to help us with this one a lot. Okay, so a question that comes up for a lot of people when they were first told what ANOVA is, that it's a way of comparing 3 or more population means, is, well, why do we need that? Because we already, back in 11.3, if you want to glance back there and see what that was, but back in 11.3, we already developed a test for comparing 2 means from independent samples. And that's what we have here. The people that, you know, if you grab one person, say in the diet group, that's independent of randomly grabbing a person from the exercise group or from the medicine group. So those are 3 independent samples. So why can't we use the test we've already got and just perform, well, we'd need 3 hypothesis tests in that case, because if I can grab a piece of paper here, I can show you. Okay, so we would need 3 hypothesis tests to find out if one is different. Here's what they would look like. So one test would have null hypothesis. Let's say we compare the results taking medicine to the results doing exercise. So if you're comparing the results with medicine versus exercise, the null hypothesis would be that the mean blood pressure reduction is the same. The alternate hypothesis would be that they're not the same. Then you'd have another test in which you'd compare, let's say we compare this time the medicine results with dietary results. So H naught would be that the mean blood pressure reduction using medicine is the same as with diet. The alternate hypothesis would be not the same. And then we've got one more comparison to do. We've compared the means for the medicine takers with both the exercise doers and the diet eaters. What we haven't compared yet is the people that did the exercise versus the group that ate the special diet. So that would be our 3rd test. And again, the null hypothesis would be no different. So the null hypothesis would be that the mean blood pressure reduction of the exercise group is the same as the mean blood pressure reduction of the diet group. And then the alternate hypothesis, as always, would be not the same. Okay, so it seems like we should just be able to, I mean, it's a little cumbersome, but believe me, ANOVA is cumbersome too. This probably wouldn't be much, if any, worse. So anyway, it seems like you could just use what we already know, do multiple repetitions of it, and you would find out if one of them was not equal to the other. So why do we need ANOVA? Well, let's say we do that. So let's say we tested the above 3 pairs of hypotheses at the alpha equals 0.05 level of, what's that word? Little vocabulary check here. Yeah, we call that level of significance. Now, let's recall that alpha gives the probability of making a type 1 error. In other words, at the 5%, at alpha equals, let me just make a note up here because I maybe should have expressed this better. So at the alpha equals 0.05 level of significance, in other words, the 5% level, this 5% chance of making a type 1 error, that means there's a 95% chance of not making a type 1 error in each of those tests. So if you do each test at the 0.05 or 5% level of significance, that's your probability of making a type 1 error, so that leaves a 95% chance of not making a type 1 error in each of those tests. Now, the 3 hypothesis tests, again, I'm referring to the 3 that we laid out just above here. Since the tests are independent of each other, the probability of not making this error in all 3 hypotheses, so doing the test 3 times, I want to know the probability of not making a type 1 error, you know, in the whole in the whole process of doing the 3 tests, well, we can compute that probability. I'm just going to go off to this side. You may or may not need to write this down. You may or may not need this reminder, but remember that if when E and F are independent events, the probability of having both E and F happen is probability of E happening times the probability of F happening. Okay, so the 3 tests, and that similar, you can extend that to as many events as you want. And let me just go ahead and write down what this would look like for 3 events, because that's what we have in this case. Each hypothesis test is going to be one of our events. So the probability of having something happen for all 3 hypothesis tests, since they're independent, is the product of the probabilities of each one happening. Okay, so back to our hypothesis tests. We've said that there is a 95% chance of not making a type 1 error in each. So if I do 3 tests, the probability of not making the error 3 times is, let's see, how do I want to say this? No error in test number 1, and also making no, so to get them all 3, to get all 3 tests right, to have them all come out right, I have to make no error in each of them. I have to do that 3 times. Make no error. Have it come out right in each test. Okay, since those are independent, it's the sum of the probability, or sorry, it's the product of the probabilities, and we said each probability is 0.95. So you have a 95% chance of getting each one right. And when you multiply 0.95 times 0.95 times 0.95, what you get is 0.86. So you have 86% probability of no error in the 3 tests. But what that means, so I'm going to call that the triple test. Okay, so because I'm trying to say that we're looking at all 3 together as like a single procedure. But look at what that means. That means that we have a 14% error, a 14% probability of making a type 1 error somewhere in that triple test, in those 3 tests. That's not what you expect when you're using the alpha equals 0.05 level of significance, right? So this is so more than what we're saying. So if we say we're doing this at the 5% level of significance, but we do it 3 times, you actually end up with a 14% probability of making an error, not a 5%. And that's a bad thing. Now, you might be able to think of a way of fixing that. It's what I thought of when I first became aware of this problem. What if you didn't want such a big probability of a type 1 error doing 3 tests? Well, sure, you could just lower the alpha for each individual hypothesis test so that it would come out, so to still be what you, so that it would come out to be 5%. Okay, so let's run with that idea. Suppose we adjust for this by using a smaller alpha, so that the smaller alpha for each hypothesis test, right, so that the final alpha comes out to be the 5% we want. Well, unfortunately, a smaller alpha, in other words, a smaller probability of making a type 1 error, causes a greater probability oops, I already have the word probability, causes a greater probability of making a type 2 error. And just in case you need a reminder of what type 1 and type 2 are, because obviously those names don't really give a hint at all at what they are. If you look back at section 10.1, the language of hypothesis testing, the analogy we used was our null hypothesis was that a accused person on trial is innocent, and so a type 1 error was causing an innocent person to go to jail. The type 2 error was letting a guilty person go free. And in our justice system, we consider that type 1 error to be of much more concern, and typically you set up the type 1 error to be the one that's of the greatest concern, so you want to minimize that. But the smaller the possibility, so if you set it up so that you have a really, really small possibility of jailing an innocent person, that's going to increase the probability of letting a guilty person go free. That's what's happening here. That's what we're talking about here. So if I make the probability of a type 1 error smaller, that's going to increase the probability of making the opposite error. So in other words, the kind of upshot here is that performing more than one hypothesis test to compare means increases the probability of making an error of some kind. Okay, so yeah, you can weigh which type of error is more important to you, and how important are they, and how much error in each type can you stand. But the big picture here is that if we were to go back to just comparing means 2 at a time, we'd have to do more hypothesis tests, and that's going to increase the probability of making some kind of error. That's why we need ANOVA. That's a good stopping point. So I'm going to, we've talked about what ANOVA is for, why we need it. In the next video, we're going to talk about conceptually what is the ANOVA test, what are the ideas behind it. And I just want to give you a heads up that for that video, you will probably like to have 3 colors of pen or pencil or ink, because we're going to make some dots, and I'm going to color code them, and you're going to want to color code them so that you can see which dots are from which data set. Okay, so I'll let you go and see you in the next video.